Our universe holds a secret far stranger than fiction. Across the galaxy, not one but three suns can share a single sky, locked in a cosmic dance of unimaginable complexity. We are about to journey through 50 of the most bizarre discoveries from these triple star systems, revelations that rewrite the rules of reality as we know them. You will learn how planets can orbit three stars at once, why some stars are violently thrown into the void, and how these systems become factories for the universe's most exotic objects. What happens when a star's gravity rips apart a planet-forming disk, and could life ever exist under the light of three suns? What do you believe is the universe's most beautiful mystery? Our own cosmic backyard holds a breathtaking secret. Just over 4 light-years away, the familiar star Alpha Centauri is not one sun but three. This stellar trio engages in a gravitational tango of staggering complexity. The two brightest stars, Alpha Centauri A and B, whirl around each other in a relatively close embrace, completing an orbit roughly every 80 years. Their dance is not a perfect circle but a stretched oval, bringing them as close together as the distance from our Sun to Saturn, and then swinging them far apart. This constant, rhythmic push and pull creates a zone of shifting gravity, a dynamic environment where the stability of any planetary orbit would be constantly tested. Yet the true marvel is the third member of this family, Proxima Centauri. This small, faint red dwarf circles the central pair from an immense distance, taking over 500,000 years to complete a single, languid loop. From the vantage point of a hypothetical planet near A and B, Proxima would appear as nothing more than a particularly bright star in the sky, its gravitational connection to the system almost imperceptible, yet undeniably present. This intricate celestial ballet forces us to reconsider what a solar system can be. How could a planet find a stable orbit amidst this three-body gravitational pull? The answer lies in remarkably delicate zones, like a narrow path walked between shifting tides, where a world might survive for billions of years under the light of two suns, with a third, distant guardian watching from the void. This gravitational dance creates a truly alien class of world, the P-type planets. These are not worlds that orbit just one star or even a close pair, but entire systems. A single planet in such a system must find a stable path around all three of its suns at once. The stability required for this is almost beyond comprehension. It is not a simple circular orbit like Earth, but a complex looping trajectory that must constantly adjust to the shifting pulls of three separate gravitational masters. The slightest nudge, the gentlest tug from a passing star, could send such a world spiraling inward to be consumed by fire or flung outward into the eternal cold of interstellar space. The orbits these planets are forced into are often wildly elongated, stretched into ovals that defy our solar system's sense of order. Imagine a year that is not a predictable cycle but a chaotic journey. For much of its long orbit, the planet would be a frozen wasteland dwelling in the outer darkness. Then it would swing perilously close to all three stars at once, experiencing a brief, scorching summer where multiple suns blaze in its sky. The very concept of seasons becomes meaningless. There are no regular patterns, no gentle spring or autumn, only extreme and unpredictable shifts between deep freeze and fiery inferno. This is the precarious existence of a planet with three parents, a world forever walking a tightrope in the cosmos. The gravitational tightrope these planets walk is mirrored by the stars themselves. Within a triple system, the dance is not always stable, and the consequences can be catastrophic. A seemingly gentle gravitational nudge between the three stars can amplify over time, building into an unstoppable chain reaction. This chaotic interaction often ends with one star being violently expelled, catapulted from its family at speeds that can exceed 1,000,000 miles per hour. In a single, explosive event, a stellar trio becomes a duo and a runaway star is born. these cast-out suns become solitary travelers hurtling through the galaxy's interstellar voids. They carry with them the unmistakable signature of their violent birth, their immense velocity a permanent scar from the gravitational battle they lost. One of the most famous examples is a star known as GW Orionis, a brilliant, hot blue star that is currently blazing a path through space as if pursued by some unseen force. Astronomers have traced its trajectory backward, finding it likely originated in the Orion Nebula, flung away from its siblings in a similar gravitational confrontation millions of years ago. The system left behind is forever changed, the remaining two stars, having shed the disruptive influence of the third, often settle into a much tighter, more stable binary orbit. Their destiny is now one of quiet companionship, a stark contrast to the chaotic trio they once were. This single, dramatic ejection fundamentally rewrites the future of the entire system, determining what kinds of planets might form and whether any could ever hope to harbor life. The violence of stellar ejections is matched only by the subtle chaos of creation. Far from tearing a star away, the triple gravity of a system can instead sculpt the cradle of planets into impossible shapes. In the system known as GW Orionis, we have a front-row seat to this celestial demolition. Here, three young stars are not just dancing together, they are actively warping the vast disk of gas and dust that swirls around them. This protoplanetary disk, which in a single star system like our own would be a flat, orderly pancake, has been ripped apart. The gravitational tug of war between the three stellar siblings has torn it into three distinct, glittering rings, each tilted at a different, bizarre angle. It is as if a master potter took a perfectly symmetrical clay pot and twisted it into a cosmic pretzel. This is not a static sculpture, it is a live action view of gravitational forces warping the fabric of a future solar system. The innermost ring is tilted so dramatically that it is practically perpendicular to the outer rings, a configuration that defies all our simple models of how planetary systems form. Within these twisted rings, the very process of planet birth is thrown into chaos. Dust grains that would normally gently clump together to form planets are instead flung onto wild, colliding paths. Any planets that do manage to coalesce here will be born into orbits of extreme and constant turmoil, circling their three suns on paths that are permanently misaligned with the rest of the system. This cosmic whirligig demonstrates that the architecture of a triple star system is born from conflict, a permanent state of gravitational tension that carves alien patterns into the raw material of new worlds. Standing on the surface of such a moon would be to experience a sky in constant motion. Your world would orbit a giant planet, which in turn would weave its own path around not one but three suns. The result is a light show that defies all earthly rhythms. You would not have a simple sunrise and sunset. Instead, the suns would rise and set at different times, sometimes alone, sometimes in pairs. Your day could begin with the soft, red glow of the smallest star cresting the horizon, only to be joined hours later by the brilliant white light of the two larger companions. The very quality of light would shift moment by moment, casting a kaleidoscope of colors and an ever-changing number of shadows from every object. You could see three distinct shadows of yourself, each one pointing in a slightly different direction as the suns march across the alien sky. But the true spectacle would be the sunset. Imagine watching one star, a brilliant orange orb, begin to sink below the horizon. As it vanishes, the sky is still bright with the light of its two siblings. Then the second star follows, painting the clouds in hues of purple and deep blue. Finally, the third and last star descends, and only then does true darkness fall, a triple twilight that stretches the evening into a long, slow fade to black. This daily celestial dance would make the very concept of time fluid and unpredictable, a constant reminder that you are living in the heart of a gravitational masterpiece. This delicate orbital dance is governed by a hidden gravitational hand, a phenomenon known as the Kozai-Lidov mechanism. In the relative simplicity of a two-body system, an orbit tends to remain stable, its tilt and its oval shape staying constant over millions of years. But introduce a third gravitational master, a distant star perpetually tugging from an inclined angle, and everything changes. This third star's persistent influence acts like a constant, subtle push on the planet's entire orbital plane. Over vast stretches of time, this does not create a gentle rocking motion, but a violent, cyclical transformation. The Kozai-Lidov mechanism forces a trade-off between the orbit's shape and its tilt. For thousands of years, a planet's path might become more and more circular while its orbital plane tilts dramatically. Then the cycle reverses. The orbit flattens into an extreme, needle-thin ellipse while the tilt decreases, pulling the planet's path closer to the original plane. This is not a calm oscillation, it is a gravitational pump, relentlessly exchanging eccentricity for inclination and back again. A world that began with a mild, Earth-like orbit can, through this process, be yanked into a path that brings it terrifyingly close to its central stars before whipping it out into the frozen outer reaches of the system. It is a cosmic game of gravitational ping-pong where the planet is the ball, and the outcome is often a final, fatal serve directly into a star or a powerful throw straight out of the system entirely, leaving a cold, dead world to wander the galaxy alone. This mechanism reveals that even orbits we perceive as stable are merely in a quiet phase of a much longer, more violent cycle. A cycle that can turn a habitable world into a scorched cinder or an interstellar iceberg. The relentless gravitational pumping of the Kozai-Lidov mechanism makes the very idea of a stable, life-friendly world seem impossible. Yet against all odds, astronomers have found one. Nestled within a triple star system lies a planet known as KY5ab, a world that resides in what we call the habitable zone. This is the theoretical region where temperatures might be just right for liquid water to exist on a planet's surface. But in a system with 3 suns, this concept is turned on its head. The habitable zone is not a static, gentle band. It is a chaotic, pulsating region that breathes and shifts with the complex dance of its stellar masters. The planet receives not one steady stream of light and heat, but a constantly changing blend from 3 different sources. One moment it might be bathed in the intense glare of a close binary pair, the next it could be relying on the dim, crimson warmth of a more distant red dwarf. This creates a climate of extreme unpredictability where the definition of a temperate orbit is rewritten daily. The planet's own path, likely shaped by the same gravitational forces that warp its neighbors, would have to be exquisitely fine-tuned to avoid being tossed between scorching proximity and frozen exile. The discovery of such a world forces us to ask what life, against all conceivable odds, could possibly emerge here. Would biology evolve to withstand wild temperature swings that could see liquid water boil and freeze within a single chaotic year? Perhaps life would retreat deep underground or into the planet's oceans, using the water as a buffer against the sky's violent mood swings. Photosynthetic organisms would face an impossible choice, needing to adapt to 3 different types of sunlight, each with its own unique color and intensity. The very rhythm of life would be alien, with sleep and activity cycles tied not to a single sun, but to the ever-changing positions of a stellar trio. A day might last for weeks, followed by an equally long night, or be punctuated by brief, confusing periods of multiple sunrises and sunsets. On such a world, the sky itself is a chaotic clock, and survival would depend on an organism's ability to embrace perpetual change. This cosmic chaos even gives stars their own distinct pulse. Deep within these triple systems, astronomers have discovered a special class of binary stars whose light doesn't shine steadily. Instead, it pulses with a rhythmic beat, a celestial heartbeat recorded in their light curves. These heartbeats are not caused by the stars themselves, but by their gravitational embrace. As the two stars in a close binary pair orbit one another, their immense gravity stretches and squeezes them, distorting their spherical shapes into tidal ovals. This constant, rhythmic deformation causes their combined brightness to rise and fall in a predictable, repeating pattern, a clean and steady pulse against the dark backdrop of space. Now introduce a third star to this delicate dance. The distant gravitational pull of this third body acts as a persistent metronome, subtly altering the rhythm of the binary's heartbeat. It doesn't just add noise, it creates a complex, layered signal. The steady pulse begins to waver, gaining slight wobbles, periodic speed-ups, and slow-downs that are imprinted upon the light like a musical composer adding syncopation to a simple drumbeat. For astronomers, this modulated signal is a goldmine of information. By meticulously decoding these tiny variations in the heartbeat, they can perform a kind of cosmic weigh-in. They can deduce the precise masses of all three stars with incredible accuracy, something that is often impossible to measure directly. They can also map out the entire system's orbital architecture, calculating the tilt of the third star's path and its exact distance from the central binary. This stellar cardiogram turns the entire system into an open book, written in the language of gravity and light, revealing secrets that would otherwise remain locked away in the silent darkness. These intricate gravitational dances leave behind a permanent record, written not in stone but in dust. Many triple star systems are enveloped by vast, glowing disks of rocky debris, the leftover building blocks of planets that never were. In a calm, single-star system like our own, this dust and rubble would slowly and peacefully clump together, eventually forming asteroids, comets, and whole new worlds. But the constant gravitational stirring from three stars makes this peaceful assembly impossible. Instead of a quiet construction site, the disk becomes a chaotic, high-speed demolition derby. The competing gravitational tugs from the stellar trio set the countless fragments on wildly intersecting orbits, ensuring that any two particles that drift near each other are far more likely to collide and shatter than to gently merge. These are not gentle impacts, they are violent, high-velocity crashes that pulverize rock and metal into finer and finer dust, a perpetual cycle of destruction that grinds down planetesimals before they can ever grow up. This relentless collisional environment has a visible signature. All that crashing and grinding releases immense amounts of heat, causing the entire dusty disk to glow with a fierce, warm light. Our eyes cannot see it, but to infrared telescopes, these systems shine like cosmic beacons. That infrared glow is a direct window into the system's violent history, a clear sign of a gravitational environment so chaotic and disruptive that it actively prevents the formation of planets, preserving its own dusty debris in a state of perpetual turmoil. Amidst all this gravitational chaos, a surprising sense of order emerges. The universe has a preferred blueprint for these stellar families, a design known as the hierarchical triple. Most triple systems are not a messy free-for-all with three stars tumbling around a single point. Instead, they are structured, almost like a cosmic company with a clear chain of command. The system is built around a close binary pair, two stars locked in a tight, fast orbit around each other. This dynamic duo then acts as a single gravitational unit, a pair of dancers spinning around one another on a vast stage. The third star is the distant audience member, orbiting this central pair from a much, much greater distance. It is a system within a system, a binary that behaves as one star from the perspective of its far-off companion. This elegant hierarchy is the key to stability. The close binary completes its frantic dance over a period of days or years, while the outer star takes thousands or even hundreds of thousands of years to make a single grand circuit. The immense separation dampens the disruptive gravitational tugs that would otherwise tear the entire configuration apart. It is this architectural principle that allows planets to find those precarious stable orbits, not by balancing between three equal pulls, but by navigating the combined gravity of a central binary while being gently shepherded by a distant third sun. This celestial structure reveals that even in complexity, the universe favors an elegant order, a quiet rhythm underlying the apparent dance of chaos. This elegant cosmic hierarchy is far from a rare oddity. The sheer number of triple star systems scattered throughout our galaxy is one of the most startling revelations in modern astronomy. Once considered celestial curiosities, we now understand they are astonishingly common, making up roughly 1 in every 10 multi-star systems. When you gaze at the night sky, for every pair of binary stars you see, there is a strong chance a third, more distant star is silently orbiting them, hidden from direct view but bound by gravity. This prevalence forces a fundamental rethink of how stars are born. The classic image of a single, collapsing cloud of gas and dust forming one central star is often just the beginning of the story. Inside the densest, coldest cores of these stellar nurseries, the chaos of collapse does not always lead to a solitary sun. Instead, the rotating cloud can fragment, breaking apart like a cosmic droplet splitting in midair. It is not a clean division into two, but sometimes a messy, tripartite split. The original cloud core, if it possesses just the right mass and spin, can quite naturally shatter into 3 distinct centers of gravity, each one greedily pulling in the surrounding gas to become a star. This means triple systems are not the bizarre outcome of a gravitational accident. They are a standard product of the star-making process itself, a fundamental and widespread architectural plan for solar systems written into the fabric of the galaxy. One of the most celebrated paradoxes in all of astronomy once revolved around a star named Algol, known for centuries as the demon star for its eerie, winking behavior in the constellation of Perseus. We now know this winking is a cosmic clock, an eclipsing binary where 2 stars regularly pass in front of each other from our viewpoint, but the data presented a baffling contradiction. The brighter, more luminous star in the pair was actually the less massive one, a star that had evolved more slowly. Its dimmer companion, however, was far more massive and had already aged into a bloated subgiant, a stage that should come much later in a star's life. This was like finding a frail, elderly parent being cared for by their robust, middle-aged child. It defied every model of stellar evolution, where more massive stars burn their fuel ferociously and die young, while lighter stars live for billions of years. The solution to this decades-old mystery arrived with the detection of a third star, a quiet observer in this dysfunctional stellar family. This third member was the key that unlocked the paradox. Long ago, the 2 close stars were born as a normal pair, with the more massive one evolving faster. As it expanded into its giant phase, it began to spill its own stellar material onto its smaller companion. This torrent of gas flowing from one star to the other was like a cosmic blood transfusion. The once massive star was stripped down, losing the outer layers that revealed its aged core, while the receiving star gained mass and youth, becoming brighter and heavier. The entire violent history of mass transfer, which reshaped the destinies of 2 stars, was stabilized over the eons by the gentle, steadying gravity of the distant third star. The Algol paradox was not a flaw in our understanding of stars, but a dramatic lesson in how triple systems can rewrite stellar life cycles through gravitational intervention. This same gravitational intervention can forge some of the universe's most extreme objects. Deep within a triple star system, a cosmic catapult event can create a millisecond pulsar. It begins with the violent death of a massive star, a supernova explosion that leaves behind an ultra-dense neutron star. This stellar corpse is often born with a powerful kick from the asymmetrical explosion, sending it careening through its system. In a triple system, the gravitational dance provides the perfect chaotic environment for this kicked neutron star to be captured into a wildly tight orbit around one of its surviving stellar siblings. Now the real transformation begins. the neutron star's immense gravity begins to rip material away from its companion, drawing a stream of superheated gas onto its own surface. This process does not just feed the neutron star, it acts like a cosmic whip. As this stolen gas spirals inward, it transfers an immense amount of rotational energy, causing the neutron star to spin faster and faster. Over millions of years, this relentless siphoning can accelerate the object from a few rotations per second to an almost incomprehensible 700 revolutions every single second. The result is a millisecond pulsar, a city-sized object with the mass of a star, spinning so fast that its lighthouse-like beams of radiation sweep across the galaxy with metronomic precision. These cosmic flywheels are a direct product of triple-star chaos, where a stellar death, a gravitational kick, and a cannibalistic feast combine to create one of the most accurate clocks in the universe. This blended starlight presents a cosmic puzzle of the highest order. When we point our telescopes at a triple-star system, we do not see three distinct points of light with different colors. Instead, we receive a single combined beam, a melange of every wavelength emitted by all three stars. This composite spectrum is a unique fingerprint, a beautiful but baffling data stream that holds the secrets of each stellar component. Imagine trying to identify three different singers in a choir by hearing only the single, unified note they produce together. This is the challenge astronomers face. To solve it, they use the stars themselves as clocks. As the stellar trio dances through its orbits, the individual stars are constantly moving relative to our line of sight. When one star moves toward us, its light is subtly compressed, shifting its signature toward the blue end of the spectrum. When it moves away, the light is stretched, shifting it toward red. Over time, by meticulously tracking the rhythmic ebb and flow of these Doppler shifts within the combined light, astronomers can pick out the individual voices. They can separate the deep, red bass note of a cool giant star from the brilliant, blue-white soprano of a hot, young star and the steady tenor of a middle-aged yellow star like our Sun. This spectral disentanglement reveals not just their motion, but their very nature. From the precise patterns of dark and bright lines in each separated spectrum, scientists can read the stars' temperatures, their chemical compositions, their sizes, and even their surface gravities, all from that one, seemingly simple beam of blended light. The gravitational tug-of-war in a triple system generates forces that can literally tear a star to pieces. When three massive bodies dance in close proximity, their competing pulls do not just gently influence each other, they create extreme tidal forces. Imagine the ocean's tides on Earth, but amplified to a stellar scale, where the pull is so immense it can deform a sphere of superheated plasma millions of miles across. In a tight triple system, a star is not pulled by just one source of gravity, but by two others from constantly shifting angles. This relentless, multi-directional stretching can force the star into an oval shape, no longer a perfect sphere but a grotesquely distorted egg of incandescent gas. The stress on the star's internal structure is unimaginable, building up until it can no longer hold itself together. The most dramatic result is mass transfer, where the outer layers of one star are ripped away by the combined gravity of its companions. This stolen gas does not simply vanish, it forms a brilliant, swirling river of superheated plasma, spiraling from one star to another in a cosmic feeding frenzy. This process can trigger colossal stellar flares, eruptions of energy that dwarf anything our Sun could ever produce, lighting up the system with the violence of the transfer. Over millions of years, a lower mass star caught in this gravitational vice can be completely stripped of its gaseous envelope, leaving behind only its dense, dead core as a permanent monument to the tidal forces that consumed it. These gravitational dramas can set a timer for stellar death itself. A star's lifespan is typically a steady, predictable burn governed by its initial mass. But within the chaotic embrace of a triple system, that clock can be violently fast-forwarded. The key lies in a process called stellar merger, a direct consequence of the Kozai-Lidov mechanism we explored earlier. The gravitational nudges from a distant third star can slowly, over millennia, pump the eccentricity of a close binary pair's orbit. Their path, once a steady circle, becomes a long, thin ellipse, driving them to pass terrifyingly close at one point in their cycle. During one such close passage, their mutual gravity can become overwhelming. Instead of swinging apart, the two stars' outer atmospheres touch, creating a drag that robs them of orbital energy. They spiral inward in a final, fatal dance, their cores colliding and their gaseous envelopes violently mixing. Two separate stars become one. This new combined star is now far more massive than either of its progenitors. In the stellar world, mass is destiny, and greater mass means a hotter, brighter, and tragically shorter life. A star that might have shone steadily for billions of years is suddenly reborn as a blue giant, a cosmic phoenix that burns through its nuclear fuel in a frantic blaze lasting only a few million years. Its death is as spectacular as its creation. It exhausts its fuel, its core collapses, and it erupts as a supernova, a premature stellar explosion triggered not by natural aging, but by the gravitational intervention of a third star. The resulting cataclysm would rip through the system, bathing the remaining stars in intense radiation and potentially hurling the stellar remnant, a neutron star or black hole, away on a new, solitary path through the galaxy. This gravitational chaos carves out pockets of profound stability, known as Lagrange points. In any two-body system, like a star and a planet, there exist 5 specific positions where the gravitational pull and the orbital motion perfectly balance. 2 of these points, L4 and L5, are exceptionally stable, acting like gravitational wells where matter can comfortably settle. Here, a smaller object can orbit the Sun while essentially sharing the same path as the planet, forever leading or trailing it by 60 degrees. We see this in our own solar system with asteroids locked into Jupiter's orbit, known as Trojan asteroids. Now, place this elegant concept into the turbulent environment of a triple-star system. The mind-bending possibility emerges of a Trojan planet, a world that does not orbit a star, but instead shares an orbit with one. Picture a system with a close binary pair and a distant third star. A planet could find a stable home at the L4 or L5 point of the third star's grand orbit around the central binary. In this bizarre configuration, the planet would forever lead or follow the star itself along its million-year journey. From the planet's surface, the sky would present a truly alien spectacle. The central binary would appear as a single, brilliant beacon, waxing and waning in brightness as the stars eclipse each other. And hanging motionless in the sky or moving in a tiny, lazy circle would be its stellar traveling companion, the star with which it shares an orbit, a second sun locked in a perpetual celestial dance just ahead or behind. The stability of these Trojan points is so robust that such a world could survive for billions of years, a tranquil island in a sea of gravitational turmoil, proving that even within the most chaotic dances, the universe always reserves a place for perfect, harmonious balance. The orderly spin of our own sun, its axis roughly upright to the plane of our solar system, is not a universal rule. Within the chaotic nurseries of triple-star systems, the very axes upon which these suns rotate are often thrown into disarray. We find stars spinning on their sides or even backward, relative to the grand orbital plane of their stellar dance. This profound misalignment is a fossilized record of the system's violent birth. When a single collapsing cloud of gas fragments into 3 distinct cores, each new star forms with its own initial spin, a momentum inherited from the chaotic turbulence of the nursery. The gravitational shoves and kicks exchanged during this crowded infancy can literally knock a star over, tilting its rotational axis into a permanent state of celestial disarray. This is not a minor detail, it has dramatic consequences for the star's entire life. A severely tilted spin axis dramatically alters the flow of heat from the core to the surface, disrupting the natural convection currents that generate the star's magnetic dynamo. The result can be a star with a wildly unpredictable magnetic personality, one that unleashes superflares of devastating power or generates stellar winds of ferocious and uneven intensity. These misaligned winds, blowing not from a symmetrical equator but from a tilted magnetic field, create a turbulent, lopsided bubble around the entire system, a protective heliosphere that is perpetually off balance, offering uneven shelter to any fledgling planets trying to form within its chaotic embrace. HD 188,753 became a celestial rebel that refused to follow the rules. This famous triple star system presented astronomers with a puzzle that seemed to break our fundamental understanding of how planets are born. At its heart, a sun-like star and an orange dwarf whirled around each other in a frantic dance, completing an orbit in just 156 days. A third, smaller star circled this tight pair from a greater distance. The initial data pointed to something impossible, a gas giant planet, a so-called hot Jupiter, orbiting the primary star in a blisteringly fast 3.5-day orbit. This was the center of the controversy. According to every accepted model, a giant planet could not form so close to its star. These behemoths are born in the cold, outer reaches of a protoplanetary disk, where ice and gas are abundant and then slowly migrate inward. But in HD 188,753, the gravitational fury of the close binary star would have torn apart the very disk it needed, shredding the planet's cradle long before it could assemble. The existence of this world suggested either our theories were completely wrong, or the planet was an interstellar immigrant that had wandered in and been captured, a notion that seemed equally far-fetched. For years, this system stood as a defiant challenge, a cosmic paradox that forced scientists to reconsider everything they knew about the chaotic birth of worlds in the most crowded stellar neighborhoods. The debate only deepened the mystery of what is possible when three suns rule the sky. The serene stability of a hierarchical triple is a cosmic illusion, a temporary state that can shatter in an instant. We have already seen how one star can be flung into the void, but there is another, even more violent way for a stellar trio to become a duo. This is the vanishing act, where two stars do not part ways, but instead merge into a single new entity. The stage is set by the same gravitational mechanism that warps planetary orbits, the Kozai-Lidov effect. Over millennia, the distant third star's persistent tugs can pump the eccentricity of the inner binary's orbit, stretching it into a needle-thin ellipse. On each pass, the two stars swing dangerously close, their outer atmospheres brushing against one another. This creates a frictional drag, a cosmic break that saps their orbital energy. Instead of swinging apart, they begin a final, fatal spiral. Their mutual gravity becomes an inescapable vortex, pulling them together in a last, desperate dance. The collision itself is not a sudden impact, but a grotesque and prolonged embrace. The two stars plunge into one another, their cores merging while their gaseous envelopes are violently shredded and mixed. For a brief, brilliant moment, the merger unleashes a cataclysmic burst of light, outshining the combined glow of the entire system. This flash is a cosmic birth announcement, but the energy released is not just in light. The violent coalescence shakes the very fabric of space-time, sending ripples outward as gravitational waves, a silent testimony to the stellar annihilation occurring light years away. When the fireball fades, a single, rejuvenated star remains. It is often hotter, brighter, and more massive than either of its progenitors, a phoenix born from a double death. The triple system is now a binary, its gravitational balance forever altered, and the third star is left to orbit the ghost of its former siblings. The structure of a hierarchical triple system carves out a private nursery for planet formation. While the entire system may be swaddled in a grand, chaotic disk, a single star within the trio can also hold onto its own personal disk of gas and dust, a smaller cradle orbiting just one of the three suns. For any worlds born here, their entire existence is framed by a sky dominated by two additional brilliant stars. These are not distant, twinkling points of light, but constant, looming presences whose gravity and radiation fundamentally reshape the process of creation. Within this private disk, the gentle dance of dust grains coming together is perpetually monitored by these stellar overseers. Their light bathes the disk in a harsh, multi-wavelength glow, heating it unevenly and driving powerful winds that can strip away the lighter, gaseous elements from the inner regions. The very chemistry of the disk is altered under this intense scrutiny. Ice, a crucial building block for giant planets, can only survive in the deep freeze of the far outer disk, but the extra light from the companion stars pushes this ice line much farther out than it would be around a solitary star. This means the raw materials for planet construction are sorted and segregated in a completely alien way, making the birth of a gas giant like Jupiter a far more challenging, if not impossible, feat. A planetesimal forming here does so under a cosmic spotlight, its growth constantly disrupted by the gravitational tides from its stellar neighbors, which stir the disk and set infant worlds on dangerous crossing paths. The result is a planetary system that is inherently unstable, a collection of worlds born under a watchful, multi-sunned sky that never allows for a moment of peaceful development. The gravitational turmoil of triple systems becomes a cosmic orchestra when the stars themselves are the dead remnants of stellar explosions. We are now finding that systems containing neutron stars or black holes are not just curiosities, they are gravitational wave factories. These are objects of almost unimaginable density, where a star's entire mass is crushed into a city-sized neutron star or vanishes into a pinpoint black hole. When three such massive bodies engage in their final, frantic dance, they do not just warp space with their gravity, they shake the very fabric of spacetime itself. Each orbit, each close pass, sends out ripples, literal waves in the dimension of space and time that propagate outward at the speed of light. In a stable binary system, these waves are a steady, predictable hum like a single, low note. But introduce a third compact object, and the symphony becomes incredibly complex. The gravitational pulls from three directions constantly perturb the orbits, creating a chaotic, overlapping set of frequencies. The resulting gravitational wave signal is a rich cacophony of spacetime vibrations, a unique fingerprint of the system's mass, spin, and orbital configuration. For physicists, this is more than just a signal. It is a direct line to the heart of extreme gravity. By listening to this symphony with observatories like LISA, the future space-based gravitational wave detector, we can test Einstein's theory of general relativity in ways no laboratory on Earth ever could. We can probe the very nature of these compact objects, understanding what happens to matter under pressures so intense that the rules of nuclear physics break down. Each chirp, each warble in the space-time continuum from these triple systems is a message from the edge of reality, written in the language of gravity itself. This complex stellar choreography leaves a unique signature in the light we observe. Many of the stars within these triple systems are known variables, their brightness naturally pulsing and fading over time. Yet their rhythmic changes are never simple. The presence of two stellar companions transforms a steady heartbeat into a symphony of interference. The most straightforward modulation comes from eclipses. As the stars whirl around one another, they periodically pass in front of each other from our vantage point, causing predictable, sharp dips in the combined light. But in a triple system, these dips overlap in bewildering patterns. The eclipse of the close binary pair might be interrupted by the distant third star drifting in front of both, creating a gradual, prolonged dimming that blankets the entire system. Then there are the tidal distortions. The immense gravity each star exerts on its partners literally stretches them into oval shapes. As these distorted stars rotate, they present changing amounts of surface area toward Earth. their brightness swelling and contracting not from internal pulses, but from this constant gravitational squeezing. This creates a smoother, wave-like pattern in the light curve, a gentle undulation superimposed over the sharp eclipse dips. Perhaps the most subtle effect is reflected light. The brilliant light from the hottest star can illuminate the facing side of a cooler companion, much like our moon reflects sunlight. As the stars orbit, the amount of reflected light we see changes, adding another slow, rhythmic brightening and fading to the mix. The final light curve is a layered cryptographic message. It contains the fingerprint of 3 individual stars, their orbits, their sizes, their shapes, and even their surface textures, all encoded into a single, wavering line on a graph. Decoding it is the ultimate astronomical detective work, requiring sophisticated models to separate the gentle tidal waves from the sharp eclipse shadows and the soft glow of reflected starlight, revealing the system's complete architecture from its flickering light alone. These stellar encounters act as cosmic forges, creating new elements through violence. When 2 stars in a triple system make a dangerously close pass, their gravitational embrace does more than just alter orbits. The immense tidal forces can rip material from their surfaces, creating vast, flowing rivers of stellar plasma between them. This stolen gas is superheated and compressed to unimaginable degrees, triggering nuclear reactions that would never occur in the star's calm core. In these temporary, chaotic fusion factories, heavier elements are born. Atoms like lithium, strontium, and barium can be forged in these stellar collisions, elements that are normally only created in the final, explosive death of a supernova. The stars then carry this chemical scar, their outer layers now polluted with the unique fingerprint of that violent encounter. For astronomers, this is a historical record written in light. By analyzing the spectrum of a star's light, they can detect the subtle absorption lines of these unusual elements. Finding an abundance of strontium in a star that should be calm and middle-aged is like finding gunpowder residue on someone's hands. It is direct evidence of a recent traumatic gravitational assault. This chemical pollution tells a story not of steady aging, but of sudden, transformative violence, a permanent change to a star's very composition forced by the chaotic dance of its stellar siblings. Globular clusters are the ancient cities of our galaxy, dense metropolises where 1 million stars are packed into a relatively small volume of space. Within these stellar crowds, stars do not live in quiet isolation. Their close proximity makes gravitational encounters a constant fact of life. A single star wandering too close to a tight binary pair can be captured, instantly transforming a simple duo into a complex triple system. This crowded environment acts as a stellar laboratory where triple systems are not just born from a single cloud, but are dynamically assembled through these chance cosmic meetings. The consequences of this dense packing are profound. The same gravitational encounters that create these trios also constantly perturb them. Orbits are tightened, tilted, and sent into chaotic spins, dramatically accelerating their evolution. This relentless gravitational stirring is a direct pathway to some of the most exotic objects in the universe. It can force 2 old, tired stars to merge, creating a single, hot, blue, and seemingly youthful star that stands out starkly among its ancient red neighbors. These are the blue stragglers, stellar phoenixes born from violent mergers within triple systems. The same chaotic environment can also take the dense, collapsed core of a dead star, a neutron star, and swing it into a tight orbit around a companion. From there, it begins to cannibalize its partner, spinning up to become a millisecond pulsar, a cosmic flywheel that ticks with unbelievable precision. These bizarre outcomes are not rare accidents in the quiet galactic disk. They are the expected products of a globular cluster's relentless, crowd-sourced gravity, where stellar destinies are rewritten by a simple brush with a neighbor. The stability of a triple star system is a cosmic gamble, and not every stellar family wins. For every successful hierarchical trio, countless others are born into gravitational turmoil so extreme that they tear themselves apart within a few million years, a mere blink in cosmic time. These are the failed triple systems, stellar arrangements doomed from their very first moments. The breakup is not a gentle drifting apart, but a violent slingshot event where one star is ejected at phenomenal speed, becoming a runaway star. The key evidence for these ancient catastrophes lies in tracing the paths of these solitary suns backward through the galaxy. Astronomers have found runaway stars moving at incredible velocities, and when their trajectories are mapped, they often point back to a common origin like the Orion Nebula. It is as if we are finding the scattered pieces of a stellar explosion that happened millions of years ago. The stars left behind after the ejection are no less affected. The binary pair, suddenly freed from the disruptive influence of the third body, recoils from the event, often moving in the opposite direction. This creates a cosmic crime scene where we can identify both the projectile and the recoil, telling the story of a triple system that was too chaotic to survive its own birth. These fleeting stellar families remind us that the elegant dances we observe are the survivors, the stable configurations that endured, while the galaxy is littered with the ghosts of systems that failed. Sometimes the most powerful presence in a dance is the one you cannot see. A star can be so faint, so dim, that it vanishes into the blackness of space, completely invisible to our most powerful telescopes. Yet its gravity is undeniable, and it betrays its existence by making the two stars we can see wobble. As the central binary pair moves across the sky, they do not trace a smooth, straight path. Instead, their trajectory is a delicate, sinuous curve, a slow, rhythmic swaying from side to side. This tiny, precise motion is the astrometric wobble, a gravitational signature of an unseen companion. It is as if you were watching a pair of dancers and you noticed they were not just spinning around each other, but were also slowly, subtly, moving around a third, empty point in space pulled by an invisible partner. Measuring this wobble is an exercise in extreme precision. Astronomers must track the positions of the two visible stars over years, even decades, mapping their minuscule deviations against the backdrop of more distant stars. From the precise shape and period of this wobble, they can deduce the mass of the hidden third star and the vast scale of its orbit. A long, slow wobble indicates a massive companion orbiting far away, its gentle but persistent tug guiding the central pair on a million-year journey. This is how we discover triple systems that appear to be only binaries, revealing that the silent, dark void between the stars is often filled with the gravity of hidden suns. This same gravitational chaos turns comets and asteroids into cosmic projectiles. In a stable system like our own, a vast, distant reservoir of icy bodies known as the Oort cloud sleeps in near total stillness. But around three stars there is no such peace. The combined gravitational pull from the stellar trio acts like a persistent, erratic hand, reaching into this deep freeze reservoir and plucking comets from their orbits. These icy wanderers are not gently nudged, they are violently flung sunward, transformed from silent icebergs into incoming missiles on long, elliptical paths straight toward the inner system. This creates sporadic eras of catastrophic bombardment, periods where any fledgling planet would be pummeled by a hail of comets, each impact delivering oceans of water, but also scouring the surface clean of any nascent life. The effect on asteroid belts is even more relentless. Instead of a quiet ring of debris slowly coalescing into planets, the belt becomes a perpetual collision zone. The gravity from three directions constantly stirs the rocky fragments, ensuring they are always on crossing chaotic paths. Gentle nudges that might lead to mergers in a comma system become, here, high-velocity impacts that shatter hopeful planetesimals back into dust. This endless grinding action prevents the peaceful accumulation of material, locking the asteroid belt in a permanent state of fragmentation. For any world trying to form or survive in such a system, The sky is not a serene expanse, but a shooting gallery where the gravitational dance of its suns dictates a constant, unpredictable rain of fire and ice. The turbulence of youth reaches its peak in systems of triple T-Tauri stars. These are stellar infants, still contracting from their natal cloud and glowing as much from gravitational heat as from nuclear fusion. When three such young, tempestuous stars share a system, their collective energy creates a nursery of unparalleled chaos. Each star is a maelstrom of activity, driving powerful winds that stream outward at hundreds of thousands of miles per hour. These are not gentle breezes, but supersonic gales of charged particles that collide and mingle in the space between the stars, creating vast, turbulent shock fronts that glow with intense X-rays. At the same time, each star is still greedily pulling in material from its own personal disk of gas and dust. You can picture these stars as messy, cosmic toddlers, simultaneously spitting out violent winds while trying to eat more from their own private plates. The gravitational interplay between the three young stars constantly disrupts this delicate balance. A close pass from one stellar sibling can yank entire streams of gas away from another's disk, redirecting the flow of material in sudden, violent bursts of accretion. These feeding frenzies cause the stars to flare erratically, their brightness surging as stolen gas plummets onto their surfaces at nearly a third the speed of light. This relentless gravitational sculpting during their formative years ultimately decides the final architecture of the mature system. The stellar winds carve out vast cavities in the remaining gas cloud, while the gravitational tugs determine which stars will end up in a tight binary and which will be relegated to a distant, solitary orbit. The wild, unpredictable behavior of these triple T-Tauri stars is more than just a youthful phase. It is the foundational chaos that forges the stable or unstable hierarchies we see in the galaxy today. For a planet caught in the gravitational crossfire of three suns, an unstable orbit is a death sentence. Its ultimate fate is written by the chaotic rhythm of the stellar dance, and the possibilities are all grim. The most common end is a violent ejection. A seemingly minor gravitational nudge from a passing star can amplify over time, building until the planet is flung from the system entirely. It becomes a rogue world, a dark and frozen nomad cast adrift in the interstellar void. This is not a gentle journey into the unknown, but a catapulting event that severs the planet forever from the warmth of any sun, dooming it to an eternity of deep freeze as it wanders between the stars. Alternatively, the planet's chaotic path might spiral inward. Its looping orbit, constantly perturbed, could decay until it makes a final, fatal plunge directly into one of its stellar parents. The outcome is a brief, brilliant flash of light as the gaseous giant or rocky world is torn asunder and consumed by the star, its material vaporized and added to the star's own atmosphere in a single, fiery act of cosmic cannibalism. Perhaps the most terrifying end comes from a close encounter that does not result in a direct impact. If the planet swings too near to one of the stars, the difference in gravitational pull between the side facing the star and the side facing away becomes overwhelming. This tidal force can stretch the entire world, pulling it into an oval shape until the rock and metal at its core can no longer hold together. The planet is literally ripped apart, shattering into a cloud of debris that forms a new, temporary ring around the star. This glittering field of rubble then becomes just another component of the system's dusty signature, a permanent monument to the world that once was, ground down by the very forces that gave it birth. Epsilon Lyrae, often called the double-double, offers a perfect lesson in celestial hierarchy. To the naked eye, it appears as a single, unremarkable point of light in the constellation Lyra. But even a small telescope reveals a stunning sight, two bright stars separated by a noticeable gap. Each of those two stars, when viewed with a more powerful instrument, splits again into its own pair. What seemed like one star is actually two tight binary pairs gracefully circling one another from a vast distance. This elegant structure is a scaled-up version of the hierarchical triples we have explored, a system within a system. The two binaries, epsilon Lyrae A and B, take thousands of years to complete a single grand orbit around their common center of gravity, yet the complexity does not end there. One of the four stars, the primary component of the first binary pair, is itself a mystery. Its light, when analyzed with a spectrograph, reveals a hidden rhythmic wobble. This star is not a single object, but an incredibly tight spectroscopic binary. Two stars so close they orbit each other in a matter of days and cannot be resolved by any telescope. This means the seemingly straightforward double-double is not merely a quadruple system, but a quintuple one, a hidden triple nested inside a larger, breathtaking dance of two binary pairs. It is a cosmic demonstration of how these gravitational structures can be built like intricate nesting dolls, with order and chaos coexisting on vastly different scales. These crucial cosmic explosions have a secret history of stellar betrayal. Type Ia supernova are the universe's standard candles, brilliant beacons used to measure the vast distances between galaxies because they all explode with nearly the same peak brightness. Yet for decades, the final trigger for these titanic blasts has been one of astronomy's greatest puzzles. The leading suspect is a white dwarf, the Earth-sized, super-dense corpse of a star like our Sun. Left alone, a white dwarf will simply cool and fade over billions of years. But in a triple star system, it can become a cosmic bomb. One compelling theory paints a dramatic picture of gravitational conspiracy. The stage is set with a close binary pair, one of which has already aged into a white dwarf. Their dance is stable, but then a third star, orbiting at a distance, begins its slow gravitational meddling. Through the Kozai-Lidov mechanism, the third star's persistent tugs can pump the eccentricity of the inner binary's orbit. The white dwarf and its companion, which could be a normal star or even another white dwarf, are driven into an increasingly tight and elliptical path. Their close passes become dangerously intimate. If the companion is a normal star, the white dwarf's immense gravity begins to siphon away its hydrogen gas. This stolen material piles up on the white dwarf's surface under incredible pressure and heat. Alternatively, if the companion is another white dwarf, their decaying orbit leads to a direct cataclysmic merger. In both scenarios, the result is the same. The white dwarf gains mass. This is a fatal acquisition. There is a strict limit to how heavy a white dwarf can be, a threshold known as the Chandrasekhar limit. As it approaches this point, the internal pressure and temperature skyrocket, igniting carbon fusion in its core in a runaway chain reaction. Within seconds, the entire white dwarf is consumed from the inside out in a thermonuclear firestorm. There is no remnant, no black hole, just an expanding cloud of incandescent gas and newly forged elements, scattering iron and silicon across space. This triple star pathway provides an elegant, if violent, solution to the mystery. It explains how these perfect cosmic yardsticks can be lit, not in isolation, but through the gravitational treachery of a three-body system, where a distant, quiet star ultimately signs the death warrant for its dense sibling. The outer atmospheres of these stars seethe with a restless energy unseen around our solitary sun. We call this layer the chromosphere, and in a triple system, it becomes a theater of extreme stellar weather. The constant gravitational tug of war between the three stars creates immense tidal forces, stretching and squeezing each star's gaseous envelope. This relentless kneading action does more than just distort their shapes. It tangles and amplifies their internal magnetic fields to a breaking point. Think of it as twisting a rubber band over and over, storing energy until it finally snaps. On these stars, that snap translates into colossal starspots, dark regions far larger than any sunspot we've ever observed, where magnetic fields are so strong they suppress the bubbling heat from below. The plasma surrounding these spots isn't just hot, it's superheated, reaching temperatures of millions of degrees. This isn't the gentle warmth of sunlight, but the furious energy of intense ultraviolet and X-ray radiation, a constant, invisible barrage flooding the entire system. For any hypothetical world orbiting here, this high-energy emission would be a relentless assault. It would strip away atmospheres, break apart complex molecules in the air and water, and bathe the surface in mutagenic radiation, effectively sterilizing the planet. The heightened chromospheric activity turns the space around these stellar trios into a permanent radiation storm, a clear sign that the beautiful dance of three suns creates an environment of profound and utter hostility to life as we know it. The universe reserves its most bizarre geometries for these stellar families. Among the strange architectures of triple systems, one stands out as a true cosmic anomaly: the polar configuration. Here, the dance of the stars defies all our intuitions about orbital planes. The inner binary pair does not spin in a disk aligned with the orbit of the third star. Instead, their plane of motion is tilted a full 90 degrees, standing on its edge like a Ferris wheel orbiting a central point. This creates a system where one pair of stars whirls around in a plane that is perpetually perpendicular to the grand, sweeping path of their distant companion. From the perspective of that third star, the close binary would appear to rock back and forth, its two suns sometimes passing one directly above the other in a vertical line. This polar arrangement fundamentally rewrites the rules of gravitational interaction. The Kozai-Lidov mechanism, which in an inclined system pumps eccentricity and tilt in a cyclical trade-off, is either completely suppressed or transformed into a far more gentle oscillation. The constant gravitational nudges from the third star no longer work to stretch the inner orbit into a dangerous ellipse. Instead, the unique geometry of the polar setup results in a strange kind of stability. The inner binary is essentially locked in its own private dance, largely insulated from the violent orbital pumping that would otherwise tear it apart. This does not mean the system is calm. The gravitational forces are still immense and complex, but they channel the energy into different, less destructive pathways. The long-term survival of such a system is a testament to the fact that in the cosmos, even the most extreme arrangements can find a precarious, yet enduring, balance, a harmony born from perpendicular motion. The dust that permeates these stellar families can gather into structures of breathtaking scale. Recent observations have revealed vast, dusty rings encircling entire triple-star systems, like ghostly halos on a cosmic stage. These are not the orderly, icy rings of Saturn, but colossal belts of fine debris that dwarf our entire solar system. Their origin is a puzzle written in dust and gravity. One compelling possibility is that we are witnessing the aftermath of planetary annihilation. A world that dared to form in this gravitational maelstrom could have been torn apart by the very stars it orbited. A close gravitational encounter, a tidal force too extreme, or a collision with another body sent there by the chaotic dance could have shattered a planet into billions of pieces. The resulting debris, slowly grinding itself down over eons, would form a vast diffuse ring, a permanent memorial to a world that failed. Alternatively, these rings might be primordial, a frozen moment from the system's birth. The protoplanetary disk of gas and dust that once swaddled the infant stars may have been so thoroughly stirred and heated by the three suns that planet formation was simply impossible. The dust never managed to clump together into planets, forever trapped in its basic, granular state by the relentless gravitational turbulence. The dusty particles we see today would then be the original building blocks of a solar system that never was, a construction site frozen in time, its workers forever scattered by the unruly presence of three foremen. These silent, glittering rings are a testament to the destructive power of triple stars, serving either as a graveyard for shattered worlds or a monument to creation forever interrupted. Even within the gravitational storm of a triple star system, a profound and delicate harmony can emerge. certain configurations fall into a state known as orbital resonance, a celestial equivalent of a perfectly timed musical chord. In these systems, the orbital periods of the three stars are locked together by simple whole number ratios. One star might complete exactly 2 orbits for every 3 orbits of its companion, while the outer star makes one grand loop for every 5 cycles of the inner pair. This is not a random coincidence, but a self-reinforcing gravitational agreement. With every pass, the stars give each other a consistent, gentle gravitational nudge at the same point in their orbits, a rhythmic push that actually reinforces the stability of their dance rather than disrupting it. This creates a predictable, repeating pattern that echoes through the eons, a true music of the spheres played out on a cosmic scale. This resonant lock acts as a powerful shield against the chaos inherent to 3 body systems. The synchronized tugs prevent the wild, eccentric orbits that lead to ejections or mergers. Instead of their paths being randomly pumped into dangerous ellipses, the stars are kept in a gentle, rhythmic oscillation, their gravitational influences canceling out the most destructive tendencies over the long term. A system captured in such a resonance can potentially remain stable for billions of years, far longer than its chaotic counterparts. It becomes a gravitational sanctuary, a rare pocket of long-term order where the complex interplay of 3 massive bodies transforms into a predictable, enduring ballet, proving that even the most dynamic forces in the universe can sometimes find a perfect, harmonious rhythm. Our own galaxy offers a spectacular laboratory, but the true test of universal principles lies beyond its borders. Astronomers have now successfully identified and begun to characterize triple star systems in our galactic neighbors, most notably within the Large and Small Magellanic Clouds. These irregular dwarf galaxies, easily visible from the southern hemisphere, present a cosmic environment starkly different from our Milky Way. They possess less heavy elements, the metals forged in the hearts of ancient stars, meaning their stellar populations are more pristine, composed of purer hydrogen and helium. When we find a triple system here, we are looking at a version of the phenomenon built from fundamentally different raw materials. The question is profound. Does this simpler, more primordial environment change the rules of the gravitational dance? The answer, emerging from painstaking observations, is a tentative no. The same hierarchical structures appear. We see close binaries with distant third companions, their orbits locked in the same elegant hierarchies that grant stability within our own galaxy. This suggests that the physics of gravitational fragmentation and orbital dynamics are truly universal. They do not depend on a rich supply of heavy elements, but are a fundamental outcome of how collapsing clouds of gas behave under the laws of gravity and angular momentum, a cosmic blueprint that operates the same way across the vast intergalactic void. Studying these external triples allows us to isolate variables, confirming that the chaotic beauty of 3 suns is not a peculiarity of our galactic home, but a universal symphony played on every stellar stage. The gravitational fingerprints of these triple systems sometimes reveal a deeper mystery. Astronomers have mapped orbits with a precision that borders on the impossible, yet in a few rare cases, the numbers simply do not add up. The observed dance of the 3 stars implies a gravitational pull that is subtly stronger than the combined mass of the 3 visible suns can possibly produce. It is as if an unseen hand is gently guiding their motion, a phantom mass lurking within the system. This has led to a radical, speculative idea on the farthest frontiers of astrophysics. Could some of these gravitational anomalies be explained not by a hidden star, but by something far stranger? Perhaps we are not looking at a triple system of stars at all, but a dark triple system. The theory posits a trio of massive, invisible objects made entirely of dark matter, the mysterious substance that makes up most of the universe's mass but does not interact with light. These would not be stars in any sense we understand. They would be dense knots of pure gravitational force, clumps of exotic particles orbiting one another in a silent, perfect blackness. They would emit no light, no radio waves, no X-rays. Their presence would be betrayed only by the way they warp the space around them, subtly bending the light from background stars or imparting a tiny, inexplicable drift to a nearby, visible stellar system. The concept redefines the nature of a solar system itself. Imagine a place where the central anchors of gravity are completely undetectable to our eyes and telescopes, where the only evidence of their complex dance is a ghostly tug on the fabric of space-time. While this remains a fringe hypothesis, it forces us to confront a humbling possibility. The beautiful, complex stellar trios we have catalogued might only be the visible fraction of a much larger and almost entirely dark population of triple systems, their silent dances unfolding all around us in a universe we are only just beginning to sense. These ancient triple systems are time capsules of the galaxy's youth. The oldest of these stellar trios formed when the Milky Way itself was just taking shape, composed almost entirely of the pristine hydrogen and helium forged in the Big Bang. Their very existence and their current orbits tell a story written in gravity and motion. Many of these ancient triples are found in the galactic halo, a vast spherical cloud of stars surrounding the main disk of our galaxy. Their orbits are wild and eccentric, carrying them on steep, plunging paths that take them high above the galactic plane and then diving back through the dense disk. This unique orbital signature is a fossilized record of the galaxy's chaotic assembly. They are survivors from a time when the Milky Way was a jumble of smaller proto-galaxies, constantly colliding and merging. A triple system born in one of these early fragments would have been violently flung onto a random, chaotic path during a merger, a path it has maintained for over 10 billion years. By meticulously mapping the trajectories of these ancient triples, astronomers can effectively rewind the galactic clock. They can trace these stellar paths backward to pinpoint the original locations of the long-vanished dwarf galaxies that merged to build our cosmic home, revealing the ghostly skeletons of the Milky Way's construction. The stars themselves are chemical fossils. In their outer atmospheres, they carry the specific chemical signature of the gas cloud from which they were born. The very first stars produced only the lightest elements like hydrogen and helium. Heavier elements, which astronomers call metals, were forged later in the hearts of massive stars and scattered by their supernova deaths. An ancient triple system with an extremely low metal content tells us it was among the very first structures to coalesce from the primordial gas. By comparing the chemical makeup of different ancient triples, we can create a timeline of enrichment. We can see how the galaxy's gas was progressively seeded with heavier elements, and how these elements were unevenly distributed by the turbulent merger process. A triple system acts like a sealed container, preserving the specific chemical conditions of its birth environment. Studying these stellar fossils allows us to read the early chapters of our galaxy's history, a story of violent mergers and gradual enrichment that is permanently encoded in the light and motion of three suns bound together since the dawn of time. The silent gravity of a hidden triple system can bend the very fabric of reality to send us a signal. As these three stars drift across our line of sight to a far more distant sun, their combined gravitational field warps the space around them. This transforms the entire system into a natural cosmic lens, a magnifying glass of unimaginable scale. The background star's light does not simply brighten and fade in a smooth curve. Instead, the intricate dance of three separate masses creates a complex and unmistakable pattern in the light, a signature of spikes and dips that is impossible for a single star or even a simple binary to produce. It is a gravitational fingerprint left on a beam of light that has traveled for thousands of years. This phenomenon, known as microlensing, is our most powerful tool for finding triple systems that are completely invisible to our telescopes. They could be composed of dim red dwarfs, cold brown dwarfs that never ignited, or even stellar remnants like black holes and neutron stars. All that matters is their collective gravity. By decoding the unique light curve of a microlensing event, astronomers can perform a gravitational autopsy. They can deduce the individual masses of all three bodies, map their separations, and even reconstruct the basic architecture of their orbits, all without ever directly seeing a single photon emitted by the system itself. These fleeting events, lasting perhaps just weeks or months, reveal entire stellar families that would otherwise remain permanent secrets of the dark. The invisible forces within a triple star system often scream their presence across the radio spectrum. These are not the gentle whispers of visible light, but raw bursts of energy generated by the most extreme magnetic and gravitational environments in the universe. The most precise signals come from pulsars, the spinning neutron stars we've met before. In a triple system, a pulsar's rapid, clock-like radio pulses become a tool of unparalleled precision. As the three stars dance through their complex orbits, the pulsar's signal is imprinted with the subtle tugs of its companions. The rhythmic pulses arrive at our telescopes slightly early or slightly late, a tiny but measurable drift that allows astronomers to map the entire system's gravitational landscape with astonishing accuracy. We can trace the wobble of the pulsar's path, discerning the mass and orbit of its stellar partners, all from the impeccable timing of this cosmic metronome. But the radio symphony holds more discordant notes. When two active stars with powerful magnetic fields orbit closely, their magnetospheres can violently interact. These are not calm magnetic fields, but tangled, writhing structures of immense power. As the stars swing around each other, their magnetic fields snap and reconnect, releasing colossal bursts of radio energy. These are stellar arguments written in static, short-lived eruptions that crackle across light years of space. For a brief moment, such a flare can outshine the entire system in radio waves, a brilliant, angry shout from a celestial dance that is anything but quiet. These cosmic families challenge our very definitions of star and planet. Nestled within the gravitational dance of some triple systems is a member that defies easy classification, a brown dwarf. This enigmatic object is a cosmic in-between, a failed star that never truly ignited. It forms like a star from a collapsing cloud of gas, but it simply does not have enough mass to create the immense pressure and heat required to spark sustained nuclear fusion in its core. It is too massive to be considered a planet, often dozens of times heavier than Jupiter, yet it is not a true star. Its existence blurs the lines we so carefully draw in our cosmic catalogues. In a triple system, a brown dwarf becomes a gravitational anchor, a heavyweight companion that influences the orbits of its stellar siblings just as profoundly as a true star would. From our distant viewpoint, the system appears as a standard hierarchical triple, but one of its suns is a cosmic imposter, glowing only with the faint, residual heat of its violent birth. It is a dark, cold ember nestled between the brilliant fires of true stars and the modest warmth of planets. This discovery forces us to ask what truly makes a star. Is it defined by its light, its mass, or simply by its gravitational role in the family? A brown dwarf in a triple system is a permanent reminder that nature does not always adhere to our tidy categories, creating instead a spectrum of objects that challenge our understanding of cosmic identity. A star can die only to be resurrected again and again in a cycle of cosmic horror. This is the fate of a recurrent nova, a zombie star trapped in a triple system's gravitational web. The drama begins with a white dwarf, the dense, Earth-sized core of a dead star. Left alone, it would cool and fade into a dark cinder. But in this crowded stellar family, it has a companion, a living star that has swollen into a red giant. The white dwarf's immense gravity acts like a vampire, relentlessly pulling hydrogen gas from the outer layers of its bloated neighbor. This stolen material does not gently fall onto the white dwarf. It forms a searingly hot, swirling disk of plasma, a river of stellar blood that spirals down onto the dead star's surface. There, under the crushing weight of new layers, the hydrogen piles up, compressed and heated to unimaginable temperatures. For decades, even centuries, the pressure builds in silence. Then, in a single, shattering moment, it crosses a threshold. The hydrogen ignites in a runaway thermonuclear explosion, not in the star's core, but across its entire surface. In just hours, the dead star erupts back to life, blazing with the light of 50,000 suns. From a distant world, you would witness a new star suddenly appear in your sky, outshining all others, a brilliant beacon of stellar resurrection. This is the nova, a temporary rebirth fueled by cannibalism, but this is not a one-time death. The white dwarf survives the blast. The outer layers of stolen gas are blown into space in a glittering, expanding shell, but the dense core remains hungry once more. And so the cycle begins again, with the white dwarf immediately resuming its vampiric feast, gathering fuel for its next apocalyptic outburst. The presence of the third star in the system is the cruel puppet master of this cycle. Its distant, rhythmic tugs regulate the entire process. Through the Kozai-Lidov mechanism, the third star's gravity can gently pump the eccentricity of the inner binary's orbit. This alters the distance between the white dwarf and its victim, controlling the flow of stolen gas. At times, the third star's influence might tighten the binary's embrace, forcing the stars closer and turning the gas stream into a torrent, hastening the next explosion. At other points in the grand cycle, it might pull them slightly apart, slowing the accretion to a trickle and delaying the inevitable detonation. This celestial clockwork ensures the zombie star never finds peace, doomed to repeatedly explode, fade, and feed again, its resurrection scheduled by the silent gravity of a distant sun. This relentless radiation bath might ironically carve out a sanctuary for life. While the surface of a planet in a triple system would be scoured by intense ultraviolet light, its very oceans could become a protective shield. Deep beneath the waves, where the water pressure crushes any possibility of sunlight, life would not rely on the suns at all. Instead, it could draw energy from the planet's own internal heat, fueled by the constant gravitational kneading from its three stellar masters. The same tidal forces that threaten to tear worlds apart would keep a planet's core molten and active, driving hydrothermal vents on the ocean floor. Around these volcanic chimneys, entire ecosystems could thrive in perpetual darkness, completely independent of the chaotic light show in the sky above. The concept of a habitable zone is turned inside out. A frozen world orbiting far from its suns and receiving only a faint glimmer of their combined light could harbor a warm, liquid ocean under a thick crust of ice, its inner warmth maintained solely by gravitational friction. This subsurface ocean would be a world without a horizon, a global cavern of water where the only light comes from the gentle glow of thermal vents, and the only seasons are dictated by the slow, rhythmic pulsing of the planet's own tidal heating. Could life emerge in such a place? On Earth, we find extremophiles flourishing in these very conditions, suggesting that the building blocks of biology are not confined to the gentle, sunlit surface of a calm world. The very forces that make triple systems so hostile on the surface might be the very engines that power life in the depths, creating biospheres that are not just alien in their appearance, but in their fundamental energy source, divorced entirely from the stars they orbit. This precise celestial clockwork transforms triple systems into fundamental tools for cosmic cartography. When a system contains an eclipsing binary, we are given a direct geometric view of its dance. As the two stars pass in front of each other from our line of sight, their light dims in a perfectly predictable rhythm. This timing is so exact it can be measured down to the second, providing a flawless orbital clock. But the true power emerges when this clock is combined with the astrometric wobble, the slow, rhythmic sway of the entire binary pair as they are pulled by their distant third companion. By observing this wobble over years, we can trace the binary's tiny path across the sky against the backdrop of more distant stars. This allows us to calculate the actual physical size of that grand outer orbit. We can use simple geometry, the same method a surveyor uses on Earth, to determine the distance from the central binary to its far-off stellar partner. This gives us a direct, absolute measurement of scale within the system, a cosmic ruler etched into the fabric of space itself. Astronomers then use these meticulously mapped triple systems as calibration points for the entire cosmic distance ladder. The precise distances we derive from them help to fine-tune other, fainter methods, like the period luminosity relationship of pulsating stars known as Cepheid variables. A single, well-measured triple star system, with its orbits timed by eclipses and its scale mapped by its wobble, becomes a foundational cornerstone. It helps to anchor our measurements of the distances to nearby galaxies, and by extension, the expansion rate and the ultimate scale of the entire observable universe. These stellar trios are more than just beautiful dances. They are the master clockmakers and master surveyors of the cosmos, their rhythmic motions providing the fundamental ticks and marks by which we measure everything else. This cosmic wobble is captured perfectly in a system known as GW Orionis, where the very cradle of planets is in constant, visible motion. The entire protoplanetary disk, a vast plate of gas and dust that should be spinning in a single, flat plane, is instead precessing. It wobbles slowly and majestically, exactly like a giant spinning top beginning to slow down, its axis tracing a slow circle in space. This is not a gentle drift, but a forced motion driven by the relentless gravitational torque from the three central stars. As the stellar trio dances in their own complex orbits, their combined gravity constantly tugs on the disk from multiple, shifting directions. This perpetual off-center pull acts like an invisible hand on a gyroscope, applying a steady pressure that forces the entire disk, trillions of miles across, to slowly change its orientation. It is a direct, real-time demonstration of angular momentum being transferred on a truly cosmic scale. The stars are essentially stealing a tiny bit of spin from the disk with each passing year, siphoning its rotational energy to fuel their own intricate orbital dance. This process carves profound changes into the disk itself. The precession creates immense shearing forces within the swirling gas and dust, regions where different parts of the disk are moving in conflicting directions. These are the breeding grounds for instability, where the gentle accumulation of planet-forming material is violently disrupted. The wobble can rip apart fledgling planetesimals or shepherd dust into strange, warped rings that are completely misaligned with the star's orbits. Observing this dynamic phenomenon is like watching the blueprint of a future solar system being actively rewritten by its unruly parents. It reveals that the architecture of a planetary system is not decided at birth, but is continually sculpted and often deformed by the gravitational conversation between young stars and their natal disk, a conversation that can leave entire worlds born into permanent and chaotic tilt. This cosmic dance can possess a unique handedness, a property known as chirality. Just as your left and right hands are mirror images that cannot be perfectly superimposed, so too can a triple star system be fundamentally left or right-handed. This chirality is written in the relative orientations of the star's spins and their orbital planes. Imagine a close binary pair spinning like a dumbbell. Their orbital plane defines a specific direction of rotation, clockwise or counterclockwise. Now add a third star orbiting this pair on an inclined path. The relationship between the spin of the inner stars and the orbital motion of the outer one creates the system's overall chirality. If the combined motions align in a specific three-dimensional geometry, the system is right-handed. If they align in the mirror opposite way, it is left-handed. This is not a trivial distinction. like the left and right-handed versions of organic molecules in living organisms, which can have completely different biological effects. The handedness of a triple system can dictate its long-term destiny. A left-handed configuration might channel gravitational interactions in a way that gently stabilizes the orbits over billions of years. The same system, if it were right-handed, might funnel those same forces into a destructive feedback loop where the Kozai-Lidov mechanism is amplified, relentlessly pumping eccentricity until a star is ejected or a merger occurs. This inherent chirality is a fossil from the system's violent birth, a permanent signature of the random twists and turbulence in the collapsing cloud that created it. Once set, this fundamental property acts as an invisible guide, steering the system's evolution down one of two divergent paths toward either enduring harmony or eventual self-destruction. Hollywood has long been fascinated with multiple suns, but the reality is far stranger than the fiction. The most famous example is Tatooine, a desert world with two suns. Yet science tells us a planet in a binary system would face extreme temperature swings, its orbit potentially unstable over long timescales. The idea of a stable, Earth-like world under twin suns is a beautiful fantasy, but it simplifies the gravitational chaos we now know defines these systems. More recent science fiction, like the television series The Expanse, takes a step closer to the truth. It portrays a future where humanity colonizes many worlds, some orbiting complex stars. While not always focusing on triples, the show captures the inherent danger and unpredictability of space, a theme that resonates deeply with the true nature of these stellar families. The fiction often misses the subtle horrors, the way three suns would not simply create longer days, but would warp time itself, turning years into unpredictable cycles of fire and ice. Video games, too, have begun to explore this frontier. Some space exploration games generate entire galaxies, peppering them with triple star systems where players can pilot their ships through gravitational labyrinths. These digital universes sometimes get the orbital mechanics surprisingly right, creating navigational challenges that mirror the complex paths astronomers calculate. Yet even the most advanced game cannot truly simulate the psychological impact of living under a sky with three celestial masters. The sunsets would not be a brief, beautiful event, but a prolonged, disorienting ritual where light and shadow engage in a slow, multi-hued war across the horizon. The greatest difference between science fiction and science is one of stability. Fiction gives us enduring worlds with familiar rhythms. Science reveals a cosmos of gravitational turmoil, where planets are temporary guests in a dance that often ends in fire or ice. These fictional depictions, while not perfectly accurate, serve a vital purpose. They ignite our curiosity and prepare our minds for the profound and beautiful truths that are, in the end, more astonishing than any fantasy we could invent. Our current view of these stellar families is about to be shattered. The next generation of observatories, instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope, are poised to turn our blurry glimpses into high-definition portraits. Their unprecedented power will not just find more triple systems, it will let us step inside them. Imagine being able to directly see an Earth-sized world, a pale blue dot orbiting three suns, its orbit traced with precision across the years. This is no longer science fiction. The immense light-gathering power of these telescopes will allow us to block out the blinding glare of the central stars, revealing the faint, warm glow of planets hiding in their gravitational embrace. We will not just detect these worlds, we will analyze the very air they breathe. By capturing the starlight that filters through a planet's atmosphere during its transit, spectrographs of unimaginable sensitivity will break that light into a rainbow of information. Each chemical element in the alien air leaves a unique fingerprint, a dark line in that spectrum. We will search for the telltale signs of water vapor, methane, oxygen, and other biomarkers. The ultimate question, whether life could cling to existence in such a chaotic environment, will move from philosophical speculation to empirical testing. We will know if the atmosphere of a world under 3 suns is a stable, life-nurturing blanket or a thin, scorched shroud stripped away by relentless stellar winds. The future is a detailed census of these cosmic dances, a map of countless triple systems that will finally reveal which architectures lead to planetary cataclysms and which, against all odds, might grant the fragile gift of stability. Every stellar dance must one day end. The ultimate fate of a triple star system is a slow-motion unraveling written in fire and gravity. When the stars within it exhaust their nuclear fuel, their deaths will rewrite the system's architecture for the final time. One potential endgame is a ghostly waltz of stellar corpses. The stars, having shed their outer layers, could leave behind a trio of white dwarfs, neutron stars, or even black holes. These incredibly dense remnants would continue their intricate gravitational dance, but in near total silence. Their orbits, gradually decaying over billions of years, would emit faint, whispering ripples in space-time, gravitational waves that slowly bleed away their energy until they eventually spiral into one another in a series of silent, dark collisions. A far more violent conclusion is a supernova-triggered dispersal. If one of the stars is massive enough, it will end its life in a cataclysmic explosion. The sudden, asymmetric blast can impart a powerful kick to the resulting neutron star or black hole, hurling it out of the system at tremendous speed. This instantly removes one gravitational anchor, and the recoil can fling the 2 remaining stars apart, sending them on solitary paths through the galaxy. The once-bound family is shattered in a single, brilliant flash. The quietest end is a gradual, cosmic drifting apart. Over trillions of years, the relentless gravitational tugs from passing stars and molecular clouds will act as a slow, persistent erosion. These tiny perturbations, accumulating over epochs longer than the current age of the universe, will gently loosen the gravitational bonds holding the system together. The stars, or their dead remnants, will slowly drift further and further apart, their orbits widening until the connection is finally broken. Each becomes a solitary wanderer in the deepening cosmic dark, their shared history fading into the imperceptible background of an expanding, cooling universe. These 50 journeys into the heart of triple star systems reveal a cosmos of breathtaking diversity and profound strangeness. We have navigated gravitational dances that fling stars into the void and warp the very cradles of planets. We have witnessed worlds walking a tightrope between 3 suns, their skies a kaleidoscope of shifting light and unpredictable time. These systems are not mere curiosities. They are fundamental laboratories where the laws of physics are tested under the most extreme conditions imaginable. They forge the universe's most exotic objects, from millisecond pulsars to supernova triggers, proving that chaos and creation are 2 sides of the same cosmic coin. The next time you gaze at the night sky, remember that for every solitary star you see, there are likely hidden trios performing their silent, intricate ballets in the darkness. Which of these 50 discoveries reshaped your understanding of the universe the most? Share your thoughts and your favorite cosmic mystery in the comments below. The dance is far from over, and every new observation invites us to look up and wonder what else is waiting to be found.